Let's talk about the small signal model for a common source amplifier. A common source amplifier without source degeneration is quite simple in design. We use an NMOS transistor which has its gate, drain, and source in the following locations. The input signal is at the gate. The R1 resistor, DC voltage rail, and output are tied to the drain, and our source, which is common, is grounded. Now, in order to derive the gain equation for this common source topology, we typically use what's called the small signal model. The small signal model is a linear approximation around a specific operating point or bias that allows us to treat the MOSFET like a linear device and more easily solve its gain and impedance characteristics. So how do we go from our large signal model to our small signal model? Let's compare the two side by side. Let's start by labeling our gate, drain, and source for both circuits. In the small signal model, we are only concerned with the small varying voltages and currents that ride on top of our DC bias points. So for a small signal approximation in this AC equivalent circuit, we can ground any constant voltage sources. This is why the RD resistor, which corresponds to R1, is shorted to ground in the small signal model. In contrast, our voltage found at the gate is an AC signal that changes with time. Thus, we must take it into account. In the small signal model, we have a delta VGS, which is the change in gate to source voltage in our circuit. In our AC approximation, we choose to model our MOSFET as a voltage-controlled current source, going from the drain to the source. If VGS is 0, then our MOSFET is in cutoff, and no current is flowing from the drain to the source. Our GM term attached to VGS is known as the transconductance and is a measure of how effectively the device converts a small change in VGS into a change in drain current. Finally, our R0 term is a small signal output resistance from drain to source, capturing channel length modulation effects and representing how the MOSFET's drain current varies slightly with VDS in saturation. So now that we have a better understanding of the small signal model, how do we find the gain of this common source amplifier? I'm going to use the generalized amplifier technique in order to solve for the gain. The gain of the generalized amplifier is AV is equal to negative big GM R out. So let's start by finding big GM, which is defined as the output current over the input voltage. In order to find big GM, we short V out, apply V in, and look to find the current at the output. Our current flowing in this direction will pass right by the RD resistor. There is no voltage at the output, and current tends to be pretty lazy. If there's a path with no resistance, the current will just flow in that direction. Using similar logic, the RO resistor is also out of the equation. We then reach our ideal current source, which is dependent on the gate to source voltage. VGS is equal to Vin minus 0 because the voltage at the source is grounded. This means our MOSFET is conducting in saturation and our current has made a full path through our circuit. So our output current is just equal to little gm times Vin. We can arrange this equation to solve for big GM, which is just current output divided by voltage in. This means our big GM value is just little gm. Now, in order to find the output resistance of our circuit, we need to take a different approach. This time we short our input voltage. We place a test voltage V sub x at the output, and we measure the current I sub x at the output. Once we have a value for our I sub x current, we solve for R out, which will just be equal to Vx over Ix. Essentially, we're just placing a voltage at the output, finding the current at the output, and using Ohm's law to solve for the resistance at the output. let's come up with an expression for I sub x. This time, our current doesn't pass by these two resistors because we have a voltage at the output. The current through the RD branch will just be V sub x over RD, and the current through the RO branch will just be Vx over RO. So where does our current go from here? Is there another branch for our current to go through? Remember that in order to find the output resistance of this amplifier, we shorted our input voltage. This means that VGS is just 0 minus 0, which is 0. That means there is no current conducting through this final branch, and our expression for I sub x is complete with these two terms. We now have our current I sub x in terms of V sub x, and we can solve for Vx over Ix. After some algebra, our final value for Rout is just 1 over Rd plus 1 over Ro. This resistance can be condensed, and we can say that the output resistance is just equal to Rd in parallel with Ro. So now that we've solved for big GM and Rout, we can put these terms into our gain equation to find our gain. The gain of a common source amplifier is negative GM times Rd in parallel with Ro. Now if you wanted to design a common source amplifier with a specific gain, all you would have to do is play with these parameters in order to construct your perfect amplifier. Keep in mind this amplifier takes into account channel length modulation. This is why we have an Ro term. In many cases, this Ro value is considered quite large, so Rd in parallel with Ro can sometimes just be approximated as just Rd. It all kind of depends on how accurate you want to be and how large Ro is in comparison to Rd.